Imagine driving peacefully down a modern avenue in Shanghai, in a silent Tesla, when suddenly a car ahead begins to emit dense smoke from beneath its body. In seconds, the flames spread as if someone had lit a blowtorch. No collision, no warning, just fire erupting from where the heart of electric vehicles lies. The lithium battery. That's exactly what witnesses reported on October 23, 2026, involving a Li Auto electric minivan. And this is not an isolated case. Every month, new images of EVs in flames emerge, reinforcing an uncomfortable truth. Lithium still burns, and it burns fast. However elegant and futuristic an electric car may seem, it carries with it an unstable component, ready to transform a peaceful ride into a flammable nightmare. Lithium, once the symbol of the green revolution, is now beginning to show its cracks. Not only does it catch fire easily when overheated, but it is also difficult to contain. Firefighters around the world now use giant containers filled with water to try to cool burning batteries, a procedure that can take hours, is expensive, and wastes thousands of liters of water. But if the fire hazard is already frightening, what comes before the car leaves the factory is even more alarming. To extract a single ton of lithium, more than 2 million liters of water are needed, the equivalent of what 10 families consume in an entire year. This water comes mainly from the Lithium Triangle in South America, a region that includes Chile, Bolivia, and Argentina. Ironically, this is one of the driest regions on the planet, and every drop sucked from the subsoil pushes local communities closer to total scarcity. And if the impact on the water isn't enough to grab attention, just look at the soil. Farmers in the region report that soil salinity is rising dangerously. Traditional crops, such as corn and potatoes, are withering even before harvest. This means that your car battery could be directly linked to the hunger of a family on the other side of the continent. The promise of a clean future, in this case, comes with a trail of destruction hidden under the hood. And here's the detail that almost no one mentions. Most of these batteries will never be recycled. Only about 5% of lithium batteries worldwide are fully reused. The rest? It ends up in landfills or is incinerated, generating new environmental risks and releasing toxic substances in the process. What seems to be a solution for the planet may actually just be shifting the problem to places where no one is looking. Or worse, where no one cares. If someone were to say aloud that driving an electric car could be just as polluting as a gasoline-powered car, they might be accused of being an environmental heretic. But when you consider the invisible impact of mining, rampant water use, and poor waste management, that comparison begins to make more sense than you'd like to admit. The difference is that the damage is now happening far from our sight, buried in distant deserts, or on the banks of rivers contaminated with heavy metals. Even with these problems, the EV market continued to grow as if nothing were wrong. Tesla, BYD, Rivian, and so many others rushed to meet explosive demand, while lithium batteries continued to be treated as the only viable option. But the fire under the car and the dry soil of Andean communities are beginning to scream louder. The question that is beginning to echo in the streets and forums is, how long will we close our eyes? Looking at the history of lithium-ion batteries, a curious paradox emerges. They were the foundation of everything that enabled the electric revolution, but now they are also the main obstacle to this revolution advancing sustainably. The cycle that once seemed virtuous, electrify, decarbonize, save energy, has become unsustainable, expensive, and in some cases, even dangerous. Predatory mining, low recycling rates, and the imminent risk of fires are just the surface of a much deeper problem, involving ethics, geopolitics, and even human rights. Imagine, for example, a single brand-new electric car, weighing almost 1,300 pounds in battery alone. When that battery reaches the end of its lifespan, which happens on average after 8 to 10 years, It becomes a 600-kilo problem that nobody knows exactly how to deal with. Separating lithium from cobalt, nickel, and graphite requires expensive technologies and dangerous processes. Therefore, most people simply discard it, and what was meant to be a symbol of a clean future becomes toxic and persistent waste. That's without even mentioning that when a lithium cell fails, the damage is instantaneous. Internal temperatures can exceed 500 degrees Celsius in a few seconds. It's like having a grenade hidden under the seat. That's why many fire departments have adapted their operations to deal with electric cars on fire. In some countries, specialized trucks carry immersion tanks to submerge the car for up to 24 hours. A disproportionate apparatus for something that should only be a means of transportation. Another issue that is rarely discussed is the critical dependence on certain minerals, such as cobalt and nickel. Cobalt, in particular, carries a heavy history. A large part of the world's production comes from the Democratic Republic of Congo, where frequent reports point to child labor, lack of safety equipment, and extreme exploitation. The supply chain that begins in such precarious conditions ends in the luxury cars of large metropolises, where no one imagines, or prefers not to imagine, what lies behind so much technology. And then another, even more strategic problem arises: geographic concentration. More than 70% of lithium and 60% of cobalt come from 3 countries: China, Chile, and Congo. A single embargo, a strike at a mine, or a new international sanction is enough to cause the global supply to collapse. This is exactly what happened between 2020 and 2022, when the explosion in demand caused the price of lithium to rise 5-fold. Car manufacturers had to delay models, revise prices, and cut investments. Not due to a lack of technology, but because of the fragility of the material base. This whole scenario puts the industry in check. Even though Tesla, for example, invests heavily in efficiency, artificial intelligence, and factory automation, it still depends on raw materials whose origin is increasingly under scrutiny. And sooner or later, consumers will begin to demand transparency not only in the car's performance, but also in the impact it causes even before it leaves the assembly line. Sustainability can no longer be a promise on the company's website. It needs to be visible in the process, in the materials, and in the choice of chemicals. What we see is that it's not just about replacing fossil fuels with electricity. Electrification itself solves nothing if the fundamental pillar, the battery, is built on an extractive, polluting, and unstable logic. And that's what makes the discussion about new chemistries, like aluminum ion, so urgent. The problem isn't the cars themselves, but the invisible foundation that sustains them. And that foundation is crying out for change, not with words, but with data, accidents, scarcity, and global imbalance. Aluminum, incredibly enough, has always been around, underestimated. Present in soda cans, airplane parts, and kitchen windows, this cheap and abundant metal is now starting to attract attention as the #1 candidate to replace lithium in electric car batteries. And it's not just because of the quantity. Aluminum is the second most abundant metal in the Earth's crust, behind only iron. It's practically everywhere: rocks, clays, recyclables, urban scrap. This means that the whole world has access to it, without needing to depend on conflict zones or environmentally fragile regions. The most impressive thing, however, is that aluminum can be recycled infinitely without losing quality. Unlike many metals that degrade or lose properties when reused, aluminum returns to its original state with only 5% of the energy required to extract it from nature. In simple terms, you can melt down a can and turn it into a battery without it losing efficiency. And doing so costs almost nothing in energy, which, on a global scale, means billions of kilowatt-hours saved per year. This is a game-changer. While lithium batteries continue to generate mountains of technological waste and require ever-increasing mining, aluminum offers the opposite logic. The more it is recycled, the cheaper and cleaner the process becomes. Imagine a world where batteries are not discarded, but reintegrated into production lines as a valuable raw material. This is the promise behind aluminum-ion batteries, which are beginning to gain traction precisely because of their ability to close the loop. The famous concept of a circular economy that everyone preaches, but almost no one truly applies. Another key point is that, unlike lithium, aluminum does not need cobalt or nickel to function. This eliminates two of the most controversial ingredients in the current battery formula. Without cobalt, the link to child labor in Congolese mines disappears. Without nickel, the production of acidic waste that contaminates rivers and crops in various regions of Indonesia is avoided. The absence of these elements transforms the aluminum battery into a solution that is not only cleaner, but also much more ethical, something that is increasingly weighing on the purchasing decisions of those seeking real sustainability. And there's more. The aluminum supply chain is much more distributed. Virtually every country can produce, process, or recycle aluminum autonomously. This eliminates the geopolitical concentration that so plagues the EV sector. Instead of depending on 3 or 4 strategic countries, the industry can spread globally, balancing prices, reducing risks, and allowing for much more stable production. This is a relief for automakers and governments that currently live under the constant threat of fluctuations in the lithium market. Now, consider the scalability of this. With aluminum being extracted locally and recycled almost in an infinite loop, battery production not only becomes cheaper, but also faster and less polluting. Gigafactories can become self-sufficient centers, where scrap metal goes in and ready-to-use batteries come out. No trucks crossing continents, no ships loaded with painstakingly extracted ore, no controversial environmental permits. It's a silent revolution, and perhaps for that very reason, even more powerful. The most surprising part? This technology is already in advanced testing stages. Some startups and universities have already demonstrated functional prototypes. And, behind the scenes, rumors indicate that Tesla has been carefully studying the viability of these batteries since 2023. If Elon Musk gives the green light, the transition could be much faster than imagined. After all, when it comes to large-scale innovation, few companies have the ability to make the future happen as quickly as Tesla. When it comes to safety, aluminum-ion technology represents a leap forward that lithium has never been able to match. While current batteries rely on highly flammable organic solvents, aluminum technology relies on stable ionic solid or liquid electrolytes that simply do not catch fire. In laboratory tests, when an aluminum cell was punctured or crushed, the reaction was almost disappointing. It only became lukewarm. No explosion, no smoke. The temperature barely exceeded 100 degrees Celsius. Compared to the 500 degrees Celsius of a collapsing lithium cell, the difference is simply brutal. This thermal stability completely changes the risk scenario in accidents. Imagine a pileup on a highway involving several EVs. With lithium batteries, firefighters would go on red alert, with lengthy and expensive protocols. With aluminum-ion batteries, the focus could return to rescuing victims, without the constant fear of secondary explosions. This is not only safety for drivers, it's also a victory for all emergency services, which have been asking for more predictable and safer batteries for years. Furthermore, aluminum does not release toxic gases when heated. One of the major dangers of burning lithium batteries is the release of hydrogen fluoride, a corrosive gas that attacks the respiratory tract and can be fatal. In urban environments or tunnels, this type of leak can be disastrous. Aluminum cells, on the other hand, do not generate this type of byproduct, even when pushed to their limits. This raises the safety level to levels that until now were only dreamed of by the automotive industry. And the difference doesn't stop there. Aluminum batteries don't suffer from the same type of thermal runaway that plagues lithium. A failure in a single lithium cell can trigger a chain reaction that affects the entire module in a matter of seconds. In the case of aluminum, the failure is contained. The material simply doesn't have the same explosive behavior, which prevents cascading fires. This changes the vehicle's engineering. Less armor, fewer containment systems, less weight, and more usable space for design. This advancement in safety opens up entirely new possibilities. Autonomous taxis, for example, which need to operate for extended periods in densely populated areas, could run on lighter, safer batteries with less legal risk. The same goes for electric school buses, delivery vehicles, and compact family cars. The fear of parking a car in a closed garage or leaving it charging overnight disappears when you know that the energy system inside is virtually harmless in the event of an accident. From a maintenance and transportation standpoint, this also represents a turning point. Lithium batteries require special handling, including strict regulations for air transport. Aluminum batteries, on the other hand, could be shipped much more easily, eliminating bureaucracy and reducing logistics costs. The simple fact that they are not classified as hazardous cargo opens up a range of applications and distributions that are currently financially unfeasible. For the end consumer, peace of mind becomes as valuable as the car's range. Knowing that the vehicle doesn't carry a constant risk of spontaneous combustion changes the perception of value, and even those who have never been involved in an accident feel the relief of owning a less volatile, less toxic, and more reliable technology. This generates loyalty, word of mouth, and above all, trust, something that no advertising campaign can manufacture. From a financial standpoint, switching from lithium to aluminum represents not just a change of material, it's a shift in industrial logic. Today, the most expensive component of an electric car is the battery, accounting for up to 40% of the vehicle's total cost. With lithium prices fluctuating drastically, automakers are treading on eggshells. Aluminum, on the other hand, being widely available and inexpensive, allows for an estimated cost reduction of around 25% per kilowatt hour. Does that seem like a small amount? On Tesla's production scale, this equates to billions in savings per year. Let's take a practical example. The highly anticipated Tesla Model 2, expected to arrive with a 40 kWh battery, would currently cost around $5,000 for that part alone. But with aluminum-ion technology, that value could drop to around $3,700. This would allow them to sell the complete car for just as $13,500, a historic feat. After all, this price puts Tesla in a position that no other automaker has managed to achieve so far, offering a true EV for less than $15,000. And we're not talking about a stripped-down, technology-free car. This entry-level model could come equipped with basic autopilot, software updates, predictive driving AI, and integration with the Tesla ecosystem. It would be like buying a smartphone on wheels, but at the price of a mid-range phone. And the most interesting thing, without depending on government incentives or ecological subsidies, just the result of efficient engineering combined with fairer raw materials.